Okay, so we've got acceleration, which is an old friend. We've got a new idea of force, which we're being really careful of because we know we can get tricked. Our human mind can get tricked on this. Force is an interaction. Some object is pushing or pulling on another object, I call it the source receiver, with some type of force. But objects, we know, it's easier to push, for example, a little kid on roller skates than an elephant on roller skates. So we'll use that as an analogy or as an example that we can imagine to understand mass. Mass is a concept that is often poorly defined in textbooks and in classes. So let's define it really carefully. It is what it is. It's something we measure. We define it. Okay? So what is mass not? Mass is not the amount of matter. It's not how much stuff. It's related if you have two baseballs, that has more mass than one baseball, right? But if you have a bowling ball, one bowling ball, that's more than a bunch of baseballs, right? It's a lot more than a bunch of ping pong balls. So it just depends. If there's a lot of ping pong balls, I suppose it'd be as much. So don't say it's the amount of matter. That really misses the point. Because the point is not bad. Okay? Mass is in fact two things. And to understand this, to miss this point is to miss a very, very deep property of physical reality. Something that Einstein brought in. We'll mention that in a second. So it's just two things. One, it's the resistance to change motion. That is, it's the resistance to accelerate. Now clearly, you got a kid on roller skates, a little kid on roller skates. You got an elephant on roller skates. You go up and push them the same amount. Who's going to accelerate more? Obviously the kid is. Who resists more? Obviously the elephant does. There's an inertia, or inertia being a resistance to change. Change motion. How? Increase speed, decrease speed, or turn. Okay, so that's what it is. It's how much it resists changing motion. And I'll show you that in a moment, one way to do it. Property number two. It is the property of matter responsible for gravity. Why? That's a cool question. So it is that, though. We'll go with that. If we go with that, we can build on it, develop an intuition. So it's two things. This is what mass is. It is the resistance to change in motion. If you have more mass, that's saying it's harder to accelerate you. Increase, decrease speed, turn. It's the inertia. And it's also something very different. Very different. It's the property of matter responsible for gravity, which is a type of this non-contact long-range force. That's a really different phenomenon. So to miss that point really misses something cool. It's called the equivalence principle. The equivalence principle. The mass, inertial mass, measured by how much it resists acceleration, is the same as for that same object. An object with a certain amount of inertial mass has that same amount of gravitational mass. It's the same quantity. So you can measure it either way. If I measure it using gravity, like on a scale, that also works for trying to speed it up or slow it down horizontally or any which way. That's deep. And you can understand that just by realizing that mass plays two roles. Two roles. Resistance to acceleration, and somehow it participates in this force, this long-range force of gravity. Let's take a quick look at that, and then we'll be good to go. All right, so if I want to measure the resistance to speeding up, slowing down, or turning, one nice tool would be a spring. If it stretches more, you know it's going to pull with a stronger force. Okay? So let's load this guy up. First check it here. Start here. I'm going to pull it out a certain amount here. Let's go right. I'm going to pull that spring out to here and see what happens. Let's go out here. See how much it accelerates. You can just get it intuitively. Okay, here it goes. and knocks down. All right, cool. Now I'm going to stretch that out the same amount. So the force on it will be the same this way. But I've loaded it up. Has it got more or less mass? It clearly resists. In fact, once it's going, it's pretty hard to slow it down. Enormous ships at sea, when they come into port, they got to start slowing down miles away. They will just keep on going. A truck loses its brakes, watch out, because it's not easy to stop that truck, right? So increasing its speed, it's hard. Decreasing its speed, it's hard. An elephant coming at you, it's hard to slow it down. It's hard to speed it up, then it's hard to slow it down. Once you get it going, it's hard to change it, and it's hard to turn it as well, okay? So this is inertial mass. How much does it stretch, or how much is required to accelerate it, speed it up, slow it down, or turn it? And I can measure it this way. I can put that on a scale. I can put my spring back here and do a little scale here, and this is a scale in newtons rather than pounds. But also I can measure mass using the second property, namely gravity. So I can take my spring and I can go like this, and I can see how much it stretches this way. And in both cases, it's stretching. And again, I can put that spring on the back of my scale and just make marks on there and name them after yourself, and you're pretty cool. So that's using the force of gravity. Clearly, the force of gravity is pulling this down, and the spring pulls it up in such a way as to balance it. So that's mass measured here on this. Now, of course, this has more mass. How do I know? Well, I look at the spring force required to hold it up, to balance that force of gravity. Okay, again, taking a look. Is it the amount of matter? Well, here's two objects. Let's see, is it the volume? No, it's not. They have the same volume, but this has more mass. Well, maybe more stuff is packed in. In essence, really, there's more protons and neutrons in the nucleus of this, and that's where the mass kind of lives, right? So, and this is aluminum, so that's one thing. It's certainly not the number of things. You go, well, two's got more than one. See that? Yeah, well, one's got more than two. So, again, it's a tricky business. One has the same as one. 1 liter of water has a mass we call 1 kilogram. 1 kilogram is a unit of mass. Kilogram or gram. Kilogram, 1,000 grams. Or in the British system, the slug, which is a really cool one. Sluggish, it's slow to change. It has inertia. Right? So that's a unit of mass. It is not force. Mass is not force. And we'll see, mass times acceleration is not force. Okay, that's critical. If you look at this definition, it does not satisfy this condition. It is not an interaction. And I'll say that now, and we'll say it more. So we've got this. Force is an interaction. Mass is what the object has, for whatever reason. I mean, you can have fun with the Higgs boson and stretch your mind there, but have some fun here. Just looking experimentally at what do people know of mass. It's the resistance speeding up, slowing down, turning. And it's responsible for gravity. And the fact that those two very different phenomena are the same property is deep. And Einstein's general relativity, warped spacetime, etc., hinges on that. So we shouldn't ignore it. We also needn't learn general relativity to appreciate that I can measure mass with a vertical spring or a scale that suspends things, balancing the force, the pull down of gravity, or I can measure mass sideways. How much does it take to speed up? Cool? Okay, keep those definitions really solid. We'll do force analysis. We'll do the 3 laws, get an intuition for the 3 laws. Then we'll do a clear method, and we'll review this stuff as we go, and you'll be masters of force analysis. All right, cool. Thanks for hanging in there.